Hi, today I'm going to introduce our work, ViTALiTy, Unifying Low-Rank and Sparse Approximation for Vision Transformer Acceleration with a Linear Taylor Tension. So, as is well known, vision transformers have achieved so-type performance in many computer vision tasks by outperforming CNNs in accuracy. The success of ViTs is attributed to its multi-head attention component that can capture global information and long-range interactions across patches of an image. In a typical ViT model, input images are first split into patches and then fed into the model comprising multiple layers of transformer blocks, and each transformer block have an MHA module, where the input X goes through a three-step computation, computing Q, K, V vectors, followed by calculating the Softmax tension S, and finally computing the tension score Z. Despite its impressive performance, ViTs are not friendly to hardware efficiency due to their required MHA modules. To better understand the underlying cause, we profile MHA modules, comprising the three steps in terms of percentage breakdown across various commercial devices, ranging from powerful and resource-rich to less powerful and resource-constrained devices. As shown in this figure, we observe that softmax tension is the most dominant slice, and it results in a runtime bottleneck and contributes 52 to 58% of the latency as device becomes more and more resource constrained. To answer why softmax tension is a bottleneck, we calculate the symptotic complexity of various computational steps in a matrix in terms of the number of patches n and the dimension per head d. It can be seen that computing and storing QK transpose has quadratic complexity in n, which is typically much larger than d, thereby resulting in challenges such as limiting ViT's efficiency and scalability, and therefore prohibit ViT's deployment on resource-constrained devices. Various algorithm-level works have been designed for ViTs, from new ViT models to ViT compression techniques to reduce the time and space complexity. However, all of this work adopt the softmax tension, which inherently has the quadratic complexity. In the hardware community, emphasis has been given to language-based transformer accelerators, where the goal is to introduce sparsity in approximating the softmax tension. However, these works rely on dynamic complexity at runtime that generally leads to non-trivial overhead in hardware design for inference. Moreover, there is a missing gap in the literature for co-designing efficient ViT-based accelerators, where the image data is of fixed size and tends to show spatial and local correlations compared to language data. So we motivate our work by posing the following question: can we more effectively approximating softmax tension with linearized tension? Well, in response to the question, we propose ViTALiTy. So at the algorithm side, we propose a linear tension algorithm and training pipeline that unifies low-rank and sparse approximation. At the algorithm side, we exploit the low-rank component without introducing any runtime sparsity. So major highlights of our work are that we are the first co-designed ViT work leveraging low-rank linear tension, and we achieved higher accuracy than existing linear attention works, and we achieved 3 times efficiency boost than SOTA accelerators. Here we first go over the proposed ViTALiTy algorithm. So first, the softmax is simply a special case of similarity measure between the Q matrix and the K matrix by using matrix associative property, where K matrix and V matrix are multiplied first, leads to an attention with linear space and time complexity. However, softmax operation impedes such reordering, which motivates our following approximation. So based on the findings, we propose the Taylor tension. Here, we first represent softmax tension as Taylor expansion comprising first-order approximation and higher-order terms. So following this decomposition, we can answer the following question. So what is softmax tension actually capturing? Well, we identify that it inherently captures both weak and strong correlations between Q matrix and K matrix. More specifically, we find that after mean centering of keys, up to 67% of the similarity scores lies in -1 to 1. These are dense and weak correlations, which are represented by the first-order approximation, while the remaining 33% similarities lies outside -1 to 1 with high magnitude, corresponds to sparse and strong connections, represented by higher order terms. This motivates us to avoid the quadratic complexity of softmax tension through directly use the low-rank approximation, which is essentially the first-order tile expansion. So after this tile expansion, we can use the matrix associative property to multiply Kim, transpose, and V first, and therefore achieve linear time and memory complexity. We observe that linear tile tension reduces the tension flops by 3 times to 10 times on various ViT models. However, tile tension is a double-edged sword. Despite the benefit of linear complexity, it has a couple of issues. The first issue is that directly applying the first-order approximation will cause a severe accuracy drop. So we profiled 7 ViT models. The accuracy drops from 76% to 23% on average. However, if we explicitly calculate the higher order terms, it will pose non-trivial computational overhead, and therefore negate the benefit of linear tension. To address the issue caused by explicitly computing higher order terms, our insight is to unify low-rank linear tension with sparse tension approximation of the higher order terms. So here, we apply the threshold-based pruning algorithm in Sanger to prune the higher order terms, and use the resulting sparse attention to approximate the higher order terms. The sparse attention during training helps regularize and boost the accuracy of otherwise low-rank linear tension. And we find that the sparse attention is not necessary after training is done, because sparse attention is only useful during initial training epochs, and it actually diminishes after the first 10 epochs. Based on this observation, we can directly drop the sparse attention during inference without hurting much of the accuracy. So during inference, we only have a linear tension, and we have no dynamic sparsity patterns. This enables a simple accelerator design without any need for reconfigurability. So here is an overview of a proposed algorithm. During training, we use a sparse attention to approximate the higher order terms, and during inference, we only have the linear tension. Okay, then let me introduce the ViTALiTy accelerator. So although our proposed algorithm can linearize the computational complexity and achieve 3 times to 10 times flops reduction on the multi-head self-attention layer, empirically, we find that this flops reduction may not result in real hardware speedup. On our testing GPUs, we find that the proposed linear attention algorithm only achieves 0.6 to 0.8 throughput in the attention layer. This is because by approximating the softmax tension with the proposed linear tile attention, we introduced several pre-post-processing operations as highlighted in colors in the right graph, such as mean centering, computing row sum and column sum of matrices, as well as vector matrix additions, multiplications, and divisions. By analyzing the flops and latency breakdown of the softmax tension and the proposed linear tile tension, we find that despite a small number of flops, the above pre-post-processing operations can have non-trivial latency overhead. They can contribute to about 80% of the overall latency on our testing GPUs. This is because on general computing platforms, we do not have dedicated hardware modules to efficiently compute those pre-post-processing operations, and we do not have an effective pipeline to avoid the latency bottlenecks due to no new data dependencies introduced by these operations. This observation motivates us to build a dedicated accelerator that equips dedicated hardware modules and integrates an optimized pipeline to fully leverage our algorithm's potential. So based on this motivation, our design accelerator first features with a multi-chunk design. So aside from a systolic array for computing matrix multiplications, our accelerator is equipped with multiple sub-accelerators, and each of the sub-accelerators is dedicated for one type of pre-post-processing operations. More specifically, we have 3 sub-accelerators in the red box. So the first one is a cumulative array for calculating the row sum and column sum of matrices. The second one is an add array, which can be used to compute matrix addition in centering, which is a normalization technique we use in the proposed algorithm. And the third one is a divider array for computing element device divisions, and it can support both single device division and multiple device division for computing mean centering and matrix vector divisions, respectively. To efficiently orchestrate those aforementioned sub-accelerators under the inter-operation data dependencies, our accelerator is equipped with a well-optimized pipeline. So this graph demonstrates the utilization of each sub-accelerator across time when computing the proposed linear tile tension. we find that naive sequential computing will result in large hardware bubbles, as shown in the red boxes here, and therefore leads to a low utilization rate. Empirically, we find that many pre-post-processing operations can be parallelized and pipelined. For example, computing row sum of V matrix can be parallelized with computing matrix multiplication between k hat and V. And computing k hat can be pipelined with computing matrix multiplication between k hat and V. Our pipeline leverages this opportunity of parallelization and pipelining to squeeze the hardware bubbles, and therefore leads to a greatly reduced latency. Last but not least, our accelerator adopts an optimized data flow that takes advantage of input data reuse. For example, our systolic array can share the input matrix Q when computing matrix multiplication between Qg and Qk simultaneously. Then, let me share the evaluation result. We evaluate ViTALiTy across 7 vision transformer models, and we compare it against SOTA hardware baselines, including commercial CPU, GPUs, and a customized accelerator, the Shang accelerator, which adopts sparse attention. For fair comparison, we adopted a comparable hardware budget for our accelerator and the baseline Shang accelerator. The accuracy of our proposed algorithm outperforms linear and sparse attention baselines. And this figure shows a relative speedup of the ViTALiTy accelerator compared to the 4 hardware baselines. On average, the ViTALiTy accelerator achieves 53 times, 30 times, and 2 times end-to-end speedup over CPU, GPU, and GPU baseline, and 3 times speedup compared to the Shang accelerator. In terms of energy efficiency, this figure shows the efficiency improvement of our accelerator compared to the 4 hardware baselines. On average, our accelerator achieves 115 times, 67 times, and 73 times end-to-end better energy efficiency over CPU, GPU, and GPU baselines, and 3 times better energy efficiency compared to the Shang accelerator. So to summarize, we proposed the first algorithm and accelerator co-design framework ViTALiTy for vision transformers with linear attention. On the algorithm side, we proposed the first linear attention. We proposed linear tile attention, which is of linear complexity, without largely compromising the accuracy. On the hardware side, we developed a dedicated accelerator to better exploit the energy efficiency of linear tile attention. So thank you for listening. For more details and results, please refer to our paper.